Okay, video 6. Now we're going to look at an application of this redox chemistry, which is galvanic cells, things that you more commonly know as batteries. Okay? So they're not going to look, first of all, much like the batteries that we're looking at. Okay? This gives us some evidence that there is electrons going on. Because when we measure an electric current, then what we're actually seeing is the movement of electrons. Okay? So if we can take our two half reactions and split them up and have them in two separate beakers, then we can measure those electrons going from one place to another. Okay? And this is called a galvanic cell. And even better, we can use that movement of electrons and the energy that they're given out to do things like light light bulbs or run your mobile phone in a slightly more complex environment, and it doesn't have two separate beakers, but it's the same basic principle. So what's happening here? We've separated out our oxidation and our reduction half reactions. We've put them in two separate beakers. We've got chemical energy that's converted to electrical energy, and those electrons which are going from our side of oxidation to our side of reduction, so in this case from the zinc to the copper, they are flowing through our external circuit and lighting up a light bridge. And then we've also got a piece of tissue paper which is soaked in some ionic salt, and that's going to balance out the charge with some movement of charged ions. Okay, so some terminology. The two beakers, each one is called a half cell. Strips of metal you've got in them, they're called electrodes. The metal which loses electrons and is assigned a negative charge is called the anode. A negative electrode. The metal which gains electrons is called the cathode. The liquid that's in them is called the electrolyte. The length of wire connecting them is the external circuit. And then we've got the salt bridge, which allows the movement of ions, which is sometimes called the electrolyte conductor. Now, you need to know these terms, you need to be able to use them accurately. You will need to label cells showing. So inside a galvanic cell, here's what we've got. Okay, this is what it looks like. Our half cell on the left, the zinc is being oxidized to zinc ions. Those electrons that are made are whizzing up along that red internal circuit through the light bulb, making it glow, back down to the copper electrode, okay, which is our site of reduction, so it's called our cathode. A bit of zinc was called our anode. They go down, they meet up with some copper ions, they make friends, they make a copper atom. Okay, so that copper electrode is actually going to get bigger and bigger and bigger. And just to balance out the charge, because we're losing some copper ions from the solution, from that salt bridge we get some potassium ions to replace it. And because we're making some zinc ions in solution on the left, okay, we get some, they're positively charged, we add some negatively charged ions in there, so that both beakers end up neutrally charged. Now, in the data sheet for this unit that your teacher should have given you, or maybe is about to give you next lesson, there's this list, which is called an electrochemical series. And this is a rank of the reducing strength of the elements. Okay? You need to get used to it and how it can be used. Okay? What it tells us is how readily oxidized or reduced something is. So elements that we find right down the bottom on the right. These are elements like lithium, sodium, they're ones that want to give up their electrons. Okay? They're very readily oxidized, we say. Their ions, on the other hand, are therefore almost never reduced. Their ions hate electrons and really don't want to get them. Up the other end, up the top left, things like F2 really want to gain electrons. Very, very happy doing that. Their ions, things like F-, almost never oxidized. Okay, and everything else is in between, but this is a rank order. So in a half cell, we can predict which reactions are going to occur. Okay, we've got both possibilities, so they can go forward, they can go backwards in both, but one of them's got to go forward and one's got to go backwards, because remember those electrons can't exist on their own, so they've got to go from one to the other. Okay, if you look at your series, find whichever one has the ions which are higher up. That one will go forwards. Whichever one is lower down, that metal will be oxidized, so that reaction would go backwards. Okay, so highest up goes forward, lowest down goes backwards. Okay. Some people think of it as making a Z shape. Some people think of a downhill slope, but basically highest up forward, lowest down backwards. So inside our galvanic, zinc is lower down, copper is higher up. So the copper will go forwards, Cu2+, adding some electrons, becoming copper metal. The zinc will go backwards, zinc metal will become zinc ions. Okay, and there, hey presto, we've got our two half reactions. And even better, you didn't have to balance them because all you had to do was copy them off your chart here. Which is not cheating, that is using your datasheet correctly.